This video will continue on conditional densities and conditional expected value. One of the important theorems that you may need to use in some applications is that suppose that in an experiment there are three random variables x1, x2, and x3. If x3 is hidden and you don't see it, so this is a hidden random variable, and then you may want to evaluate the distribution of x2 when you observe this one. Then you have the distribution, conditional distribution of x1 given x2, but then if there is a hidden random variable involved that you don't see it and you don't want to have it, you could use this one. The proof of this theorem is very easy. Another theorem is conditional expected value theorem, which is the expected value of the expected value is equal to the expected value. So the theorem is as follows. Suppose that you have n random variables and a conditional expected value of one given the other one. So this means that you know that x2 is equal to x2, x3 is equal to x3, and xn is equal to xn. So you know these values, and then you have these random variables. So given these events, you want to calculate mean of that. So obviously the definition for this expected value, this is abbreviation. The definition is that the value that this guy takes on, which is x1, times the conditional distribution. So obviously here, because the values of x2, x3, and xn are fixed, you have only one variable to integrate over. So this integral is over x1 to infinity. So this integral will not be a function of x1 because you integrate, you sum over x1 from minus infinity to plus infinity. But it is a function of these given values x2, x3, xn. So this is a function of this guy. This is a function of x2, x3 up to xn. So this function allows you to form a new random variable y. So this is a function of x2 to xn. So I define a new random variable. So we define. Now we want in this theorem to prove that mean of these random variable y. Okay, remember that this y is a function of these random variables. Y is a function of x2 to xn. So if you want to define mean of y, is going to be the value that y takes on, okay, and then over the distribution of that. So you could put phi of x2, x3, xn, okay, and then you have to put the distribution of x2 to xn. So you put f of x2, x3, xn, x2, and then you have to integrate it. So dx2, dx3, dxn. So this is going to be multiple integral, and all from minus infinity to plus infinity. So in this theorem, we want to show that the expected value of this one is going to be just mean of x1. In other words, if you calculate mean of x1, first conditional on x2 to xn, and then, so this is y itself is conditional on x2, and then if you substitute these guys by random variables for these random variables and take another additional integral, so remember that this is one integral, and here you have n minus 1 integrals. So in this side I have this one involves one integral and minus. So in total I have n integrals. This one is just integral over distribution of x1 or integral over the joint distribution. So this is going to be equal to n integral over x1 and a joint distribution of x1, x2, etc., x1 and so on. So the two sides are equal. In other words, the mean is equal to this is conditional mean and this is another mean. So the mean of the conditional mean is equal to unconditional mean, and the proof is very easy. So one side you could put the conditional mean and so on. So the details you could look at this. So it's kind of like here n minus 1 integrals, and then you have another one inside and you can perform it. So in this example, we'll see how this step-by-step integration or step-by-step application of expectation is important. Sometimes we cannot even do it at one shot. So in this example, consider that you have one random variable which takes discrete values, 1, 2, etc. And suppose that you have a sequence of random variables which are independent, x1, 2, etc. So you have x1, x2, x3, etc. So a sequence, it goes to infinity. And you define S to be equal to the sum of n of them. So n is one integer value, which could be 1, 2, etc. So if n is equal to 1, just S is equal to x1. If n is equal to, S is equal to x1 plus x2, etc. Now, in this example, we want to find the mean and variance of S. So what's going to be mean of S? Okay, so if I try to do that, so how could I do it? So you cannot do it at one shot. So what I do, I say I calculate mean of S first, given n is equal to, let's say, n, and then replace this n by a random variable and so on. So what I do, I calculate mean of S given n. So this expectation is over distribution of, let's say, fx1, x2, etc. And this is over the distribution of n, over distribution of n, and this is over of the sequence I equal 1 to infinity. Okay, so we do it at two separate steps, and then this is the only way. The same thing for the variance. So we first find the conditional mean of S given n. So if this n is fixed, is not random, so then this S is equal to sum of k equal 1 to n xk, and n is fixed. So because this is fixed, I could just say that mean of each of these guys is equal to mu, and then I have n of them, so I will get n mu x. So this is, now this n becomes random, so I substituted the random variable and now apply the mean over it. So I get mean of S given n becomes equal to mean of n mu x. This is constant, so I will get mu n times mu x. Now for the variance, first of all, because they are independent and have identical distribution, the correlation between xi and xk is calculated by that. So if I and k are not equal, so this is going to be mu x to the power 2, and if they are equal, then is equal to mu x to the power 2 plus variance. So this delta ik is equal to 1 if I is equal to k, and is 0 if I is equal not to k. because if they are not equal to each other, they are uncorrelated, so the mean of product becomes product of the mean because they are independent. But if I and k are equal, so this is going to be the power, which is going to be variance plus mean to the power 2. So now I calculate mean of s to the power of 2 given these events. So I apply the same concept, and in this case this s, because s is summation of, let's say, k equal 1 to n of, let's say, x of k, and then s conjugate is equal to summation of, let's say, I equal 1 to n of x I conjugate. Here I use a different dummy variable. So if you multiply these two together, so s conjugate is equal to summation over I, summation over k, and then you have xi, xk, xi conjugate, or we put the conjugate the other way. And then if you calculate mean of that, obviously given n, so you get mean of these guys. Okay, so you will get mean of these. Remember that here mean is constant because I have this condition. Okay, so this becomes constant. So I'm not worried about that because I put this condition. So this s conjugate is a double sum, and then double sum comes out of expectation, and this guy is already calculated. I put it here. Now, for those terms that I and k are not equal, this guy is 0. And for those cases that I and k are equal, these guys are constant sigma 2n. So I get n of these, and I get n2 of these, so I get this one. So this obviously simplified. Now I could calculate unconditional mean of that by taking expected value. Now this n becomes random variable. So I have to take mean of this guy when this n is substituted by a random variable. So mean of these to the power of 2 will become a mean of these. So if I apply this one, this is constant, so this will become mu x, and this will become mean of n to the power 2. So obviously you get this one. Now if you want to calculate sigma 2s, is obviously equal to mean of s to the power of 2 minus mean of s to the power of 2. So I have mean of s already here. You calculate its value to the power of 2, and then you substitute it. So this gives you mean of s to the power of 2, which is calculated here, and then minus mu n mu x absolute value to the power of 2. So you simplify it, and then you get this result. So it's kind of you substitute one in another one.